This video covers derivatives of inverse functions and also an introduction to particle motion. So for the derivatives of inverse functions, we're going to do a very specific type of questions because it gets pretty complicated when we want to find the derivative of inverse functions. So I did lay out kind of a step-by-step guide on how you're going to do this. Usually you're either given a huge table of values or you're going to be given f of x and then an x value. So if you look at our function that's given to us, if you want to find the inverse of this, that gets pretty complicated because we need to switch our x and y value and then somehow solve for y. And in this case, like I said, pretty complicated for that. So we're going to follow the step-by-step guide in finding the inverse at a specific point of x equals 1. The first step is we're going to find the magic number of some number for which f of that number is equal to the value x value we want. So in other words, our step 1, we need to find f of something is going to give us 1. And now let's look at our function. In order for this to become 1, well, for this one, if we have an x equals 1, x equals 2 in here, we're going to have a problem because it's going to be a decimal number, and we don't want that. So in order for us to not get a decimal number with e to the something, we need to have e to the 0, which means a potential x value could be 0. So tan of 0 plus e to the 0 will give us 1 because tan of 0 is 0 and e to the 0 is 1. So then our magic number is going to be 0 in this case. So 0 is the magic number. Okay, and then the second part now, we're going to find f prime of x and then we're going to use that magic number to evaluate it. So f prime of x, we're going to take the derivative of tan x and then the derivative of e to the x. So the derivative of tan x is secant squared x. The derivative of e to the x is still e to the x. And now we're going to evaluate it at 0. So f prime of 0 is 1 over, because we don't really want to evaluate secant, we can change this to cos, which is 1 over cos squared of 0 plus e to the 0. This is 1 plus 1, which equals to 2. Then our final step here, the desired slope we want is going to be the reciprocal of step 2. So our final answer, the derivative of f inverse of x, is going to be 1 over 2. Whenever x is equal to 1. Let's try a different example. And in this case, we're given a table of values instead. We're going to follow the same 3 steps though. We want to find the magic number, and in this case, g is the inverse of f, so we want to find the value of g prime of 2. That means our x value is equal to 2 in this case. So that means f of what is going to give us 2? And if we look at our table of values, it looks like f of 1 will give us 2. So the 1 is going to be the magic number. Now we want to find f prime of 1. So looking at our chart again, f prime of 1 is going to be negative 5. And then the last step is taking the reciprocal of what we just found in step 2. So the value of g prime of 2 is going to be negative 1 over 5. And then that's it. So these are the only type of inverse questions that you may want to know, because those are the only questions you're going to be asked of. In terms of taking derivatives, we are done learning about taking derivatives, at least for this course. And now we're going to look at applications of derivatives. So I'm going to introduce a particle motion question in the next page. And then in the next video, I'll do more particle motion as well as L'Hopital's rule. So looking at example on particle motion, before we begin, I want to make a point that whenever you have velocity and acceleration that goes in the same direction, or in other words, with the same sign, then the particle will be speeding up. So particle speeding up when velocity and acceleration are in the same direction. That means if velocity is positive and acceleration is positive, then you're speeding up. Or you could have a negative velocity and a negative acceleration. That object is still speeding up, just in the negative direction. Now for slowing down, this happens when the velocity and your acceleration have opposite signs. So that means that if you have a positive velocity and a negative acceleration, you're slowing down. If you have a negative acceleration and positive velocity, you are still slowing down. All right, so let's look at this example. There are quite a few parts to this, 6 different parts. So we have a particle moving along a line, and we're given its position in terms of time, which is dictated by this function here. So S is measured in meters and T is measured in seconds. If we want to find the displacement during the first 5 seconds, well, this equation gives us our position, which also gives us our displacement in a way. So for the first one, displacement is usually calculated as your first position minus your second position, or in this case is going to be your position at 5 seconds minus your position at 0 seconds, the very beginning. And then we're just going to plug this in. So if you're looking for S of 5, that's 5 squared minus 3 times 5 plus 2. Subtracted by 0 minus 0 plus 2. So really just subtracting by 2. That's 25 minus 15 plus 2 minus 2. All of this is 10 meters. So that's your displacement. If you want to find the average velocity, your average velocity is calculated as displacement over time. Should be kind of a reminder from physics. So your displacement we just calculated, which is 10 meters. And then the time, we're talking about 5 seconds. So then your overall average velocity is 2 meters per second. Instantaneous velocity is very different from your average velocity. Remember when I made you calculate m secant and m tangent? Well, similar case here. So m secant would have been your average velocity, and then m tangent is your instantaneous velocity. So if we want to calculate the instantaneous velocity, we need to take the derivative of s. And then we'll evaluate it at 4 afterwards. So we're going to find s prime of t. This is 2t minus 3. And then we're going to evaluate it at 4. Which is 5 meters per second. For D, we want to find the acceleration. Now, the relationship between your derivatives and acceleration, well, what did we find here? We found the instantaneous velocity by taking the derivative. If we take the second derivative, we are going to get the acceleration. So A of t is the derivative of our velocity equation. So we're taking the derivative of 2t minus 3, which is 2. So that means it doesn't matter what our time is, it's always going to have an acceleration of 2 meters per second squared. Okay, the next one asks, what values of t does the particle change direction? We're going to look at velocities to help us determine how this is going to change. So if we think about it, if something is moving towards the right, how is it going to all of a sudden go to the left? Because that needs to change direction. Well, at this point, that particle needs to slow down, probably hit 0 velocity, and then go the other direction. So it's going to change direction when your velocity is equal to 0. So we're going to set our velocity equation that we found in part C and then set it equal to 0 to solve for the time for when that happens. So that's 2t is equal to 3, and t will be 3 over 2 seconds. So therefore, the particle is going to be at rest at t equals 3 over 2 seconds. And we can verify this by doing a little table of values, or we can just do a sign diagram. So in this case, I'll just do a sign diagram. I'm going to look at this in terms of velocity. So if I plug a t equals 1 or t equals 0 in here into our velocity equation, we are going to get a negative number. Let's just say time is 0. That's 0 minus 3, which is negative 3. So we get a negative value for a value in there. Or I can plug in t equals 1. That'd be 2 times 1 minus 3, still a negative number. That means we're moving in the left direction. Now, if I look on the other side, I need a t value, a time that's larger than 1.5 seconds. So let's pick 2. If t is equal to 2, that's 2 times 2, which is 4. 4 minus 3 is 1. We get a positive velocity here, which means we're going to the right. So that means that t equals 3 over 2, t is equal to 1.5 seconds. The particle is going to be at rest and it will change direction. And that's because v of t changes sign from negative to positive here. And the last question, where is the particle speeding up? So if we look back at the notes that I created on the side here, if it's speeding up, we need the velocity and acceleration to be in the same direction. So we need to keep that in mind. So V and A have the same sign. Well, when we found acceleration has to be 2 meters per second squared, no matter what the time value is. So that means if acceleration is a positive number, your velocity has to be a positive number as well. So acceleration is a positive number. So velocity needs to be a positive number as well. And this would happen only when t is greater than 3 over 2. And we found that in part E. Because if it's smaller than 3 over 2, we're going to get a negative velocity.